What is the fundamental thing that separates a quantum computer from, say, the classical computer you're probably listening on right now?
Okay, the core difference really is that a quantum computer doesn't just use different components, it actually exploits well, the strange rules of quantum mechanics
The
itself.
physics is different.
Exactly. On really tiny scales, matter acts like both particles and waves. Quantum computing leverages this wave-like behavior. And because it operates on these fundamentally different physical principles, it can perform certain types of calculations exponentially faster than any classical computer could ever hope to. Classical physics just hits a wall there.
And that brings us to the qubit, right? The quantum version of a classical bit. A classical bit is simple 0 or 1, on or off.
Right, very definite.
But a qubit sounds much weirder. How does that work?
Okay, so the qubit is the basic unit of quantum information. And its defining property is something called superposition.
Superposition.
Yeah. Think of it like a spinning coin. Before it lands, is it heads or tails? Quantum mechanics says, in a way, it's both simultaneously until you actually look, until you measure it.
So it exists in this in-between state.
Precisely. It's an abstract state, sort of between the definite 0 and the definite 1. It can be a blend of both at the same time. Now, when you measure the qubit, it collapses. It has to pick one.
Ah, okay.
And the outcome, whether you get a 0 or a 1, is probabilistic. It's not predetermined until that measurement happens.
So the act of measuring changes it. But before that measurement, the state holds much more information, potentially.
Exactly. And that's where the power comes from. Quantum algorithms are designed to manipulate these qubits while they're in superposition. They use these things called complex probability amplitudes, which, unlike classical probabilities, can be negative or even complex numbers.
Right, not just positive chances.
Correct. This allows for wave interference. Just like sound waves can cancel each other out or amplify each other, quantum algorithms use interference to kind of amplify the probability of getting the right answer when you finally measure, and cancel out the probabilities of getting the wrong ones.
Clever. Guiding the probability.
Yeah. You can even visualize a single qubit state on something called the block sphere. It's a way to map all the possible superpositions.
Okay, that theory sounds incredible, almost magical. But let's ground ourselves again. Where does this stand in the real world? What's the current state of these machines?
Yeah, it's really important to emphasize that right now it's still largely experimental. These aren't practical tools for most real-world problems yet.
Okay.
There are some huge obstacles still to overcome before they move beyond specialized labs.
Right. It feels very cutting edge, very new. But you mentioned earlier the ideas have roots going back quite a way. How did quantum mechanics and computer science even start talking to each other? They seemed like such different worlds initially.
They really were for a long time. You had quantum theory taking shape in the 1920s to describe the atomic world, and then digital computers emerging after World War II. Very separate fields. But the convergence started, maybe surprisingly, when physicists began wondering if quantum mechanics itself could be a basis for computation. In 1980, Paul Benioff described a quantum Turing machine, a theoretical model.
Just showing it was possible, conceptually.
Exactly. Then, in the early 80s, you had Yuri Manin in Russia and Richard Feynman in the US independently suggesting something really key. They realized that simulating quantum systems on classical computers was incredibly hard, maybe impossible for complex systems.
Because classical computers don't think quantumly.
Right. So they proposed, what if you built hardware using quantum phenomena to simulate quantum phenomena, use quantum to understand quantum?
That makes a lot of sense. Fight fire with fire, sort of.
Sort of. And then things branched out. In 1984, Charles Bennett and Gilles Broussard applied quantum ideas to cryptography, coming up with quantum key distribution, QKD, the idea of using quantum states for truly secure communication.
A completely different application.
Totally. And then came the first glimpses of quantum algorithms showing real potential speed-ups, things like Deutsch's algorithm in 85, Simon's in 94. They demonstrated this idea of quantum parallelism using superposition to query data in a fundamentally faster way.
Okay, so the theoretical foundations were building.
Yeah.
But then came the one that really made everyone sit up, right? The encryption breaker.
Absolutely. That was Peter Shor in 1994. His algorithm showed that a sufficiently large, stable quantum computer could break the encryption methods like RSA and Diffie-Hellman that protects so much of our digital world.
Because they rely on factoring large numbers, which is hard, classically.
Exactly. And Shor showed a quantum computer could do it efficiently. That got a lot of attention. Suddenly, governments, intelligence agencies, big tech, they all started investing seriously.
I bet.
Then 2 years later, Lovegrover came up with an algorithm offering a significant speed up for unstructured search problems. And Seth Lloyd proved that quantum computers could indeed simulate quantum systems efficiently, confirming Feynman's intuition.
Wow. So a flurry of breakthroughs in the mid-90s.
Yeah, and the experimentalists weren't far behind. The first 2-qubit quantum computer was built in '98. Small, noisy, but it proved the basic concepts could be physically realized. And since then, it's been a slow, steady climb, more qubits, better control, lower error rates. Still a long way to go, but progress.
Okay, we've mentioned qubits and superposition, but how do these machines actually do the calculating? What's happening under the hood that's different from classical logic gates and electrical signals?
Right, so classical computers run on classical electrodynamics, but quantum programs need incredibly precise control over these delicate quantum systems. Mathematically, we describe quantum states using linear algebra vectors represent states, matrices represent operations or gates.
Okay, more math.
A bit. A single qubit state, like we said, can be a mix, say As plus 1 haro. And these alpha and beta, the probability amplitudes, they can be complex numbers. That's key because it allows for that destructive interference we talked about, possibilities canceling out.
Which you can't do with just positive probability.
Exactly. When you measure, the probability of getting 0 is ox and 1 is vac. That's the Born rule.
So the measurement is still probabilistic based on those amplitudes. Still sounds quite abstract.
It is. And it gets wilder with more qubits. Add just one more qubit, and you double the number of dimensions you need to describe the system state. A 100-qubit system needs, well, 2 to the power of 100 classical values to fully describe its state.
That's astronomical.
Yeah.
Way beyond what we can simulate classically.
Absolutely. And then there's entanglement.
Ah, yes, the Stucky action at a distance.
That's the one Einstein was famously skeptical about. Imagine 2 qubits prepared in a specific link state, like a Bell state. If you measure one, you instantly know the state of the other no matter how far apart they are. They're intrinsically connected. You can't describe them independently.
That connection seems vital for complex calculations.
It is. And to manipulate these states' superposition, entanglement, quantum computers use quantum logic gates. They're analogous to classical gates like NOT or AND, but they operate on qubit states using those matrix transformations I mentioned. They have to be reversible, unitary operations.
Can you give an example?
Sure. A simple one is the X gate, which is like a classical NOT gate. It flips 0 ways to 1 say, and vice versa. A more crucial one, especially for entanglement, is the controlled NOT or CO-NOT gate. It acts on 2 qubits.
Okay.
It flips the second qubit only if the first qubit is in the 1 state. If the first is 0 Li, it does nothing to the second. This kind of conditional logic is absolutely fundamental for building up complex quantum algorithms.
So a quantum computation is essentially a sequence of these carefully timed gates acting on qubits, followed by a measurement.
In the most common model, yes, a network of gates and measurements designed to harness superposition and entanglement for a specific task.
Okay, so if the information processing is so different, are there different ways to actually build or program these computers? Different models people are working on?
Yes, definitely. The one we just described, using sequential gates, is the gate array or quantum circuit model. That's probably the most widely studied. You aim for a universal gate set, a small set of gates, like single qubit rotations, plus that CNOT gate that can, in theory, approximate any possible quantum computation.
Like building anything with Lego bricks?
Kind of. Another approach is measurement-based quantum computing. Here you start with a large, highly entangled resource state, like a cluster state. Then the computation proceeds just by making specific sequences of measurements on individual qubits within that state.
So the computation is the measurement pattern.
In essence, yes. Then there's adiabatic quantum computing. This is different again. It's based on a principle called quantum annealing. You start the system in a simple, easy-to-prepare ground state, and then slowly, adiabatically, change the system's parameters towards the complex problem you want to solve. The idea is the system will naturally relax into the solution state.
Trying to let the quantum system find the answer itself.
That's the intuition. And there are more exotic ideas, too.
Like the neuromorphic and topological ones you mentioned in the outline.
Right. Neuromorphic quantum computing tries to borrow ideas from how brains work, which is quite unconventional for quantum. And topological quantum computing is maybe the most out there. It aims to use the properties of exotic particles called anynes and encode information in how they are braided around each other in 2D. The hope is this could be inherently resistant to noise.
Braiding particles.
Yeah.
Okay. That's definitely different.
It is. Now, theoretically, all these models can compute the same things. They're equivalent to a universal quantum Turing machine. But in practice, how difficult they are to build, control, and scale varies hugely.
Which brings us back to the practical side. Building any of these sounds incredibly hard. I've heard this term NISQ used a lot recently. What does that signify about where we are now?
NISQ. Right. It stands for Noisy Intermediate Scale Quantum. It's a term coined by John Preskill to describe the current era of quantum hardware.
Noisy and intermediate scale. Doesn't sound ideal.
Well, it reflects reality. Intermediate scale means we have maybe 50 to a few hundred qubits, not tiny, but nowhere near the millions likely needed for fault-tolerant computing. And noisy is the critical part.
The errors we talked about. Decoherence.
Exactly. The quantum gates aren't perfect. The qubits lose their quantum states too quickly. This noise limits the depth, the length of computations you can run before the errors overwhelm the result. So NISQ machines aren't yet fault-tolerant.
So they might be useful for some specific, perhaps near-term tasks, but they're not reliable for complex, long calculations.
That's the general idea. There's a theory, the threshold theorem, which shows that if you can get the error rate per gate below a certain threshold, you can implement quantum error correction to build truly fault-tolerant machines. But achieving that threshold and implementing the correction, well, that's often described as a rather distant dream.
Still a long way off.
So there are positive signs. There was a notable announcement from Harvard in 2023 working with DARPA, MIT, and others. They demonstrated a way to create more efficient logical qubits using better error-correcting codes. That could be a significant step in overcoming one of the biggest obstacles.
That's promising. Okay, so assuming we do overcome these hurdles, or even within ISQ machines, finding niches, what are the killer apps? What are the problems where quantum computing could really make a difference for you, the listener?
Right, the why bother question. There are several key areas. First, cryptography and cybersecurity. This is a double-edged sword. On one hand, quantum mechanics enables new forms of secure communication, like quantum key distribution, QKD, or quantum random number generators, QRNGs. These promise security based on the laws of physics, resistant to eavesdropping. That's the enabling side.
Okay, better security tools.
But then there's the quantum threat. Shor's algorithm, as we mentioned, could break RSA, Diffie-Hellman, the public key cryptography underpinning much of the internet, e-commerce, secure communications.
So it could destroy current security.
Potentially, yes. If a large enough quantum computer is built, this is driving a huge effort in post-quantum cryptography, developing new encryption methods that are resistant to both classical and quantum attacks, things based on lattices or coding theory, for example.
So we need new locks before the quantum key arrives.
That's the race. And don't forget, Grover's algorithm, it weakens symmetric encryption like AES. It doesn't break it outright like Shor does for RSA, but it effectively halves the key strength. So AES 256 becomes more like AES 128 against a quantum attacker.
Still requires doubling key lengths for the same security level.
Right. All this has significant geopolitical implications, too. Nations are investing heavily, both in developing quantum capabilities and in defending against the threat. It's a new dimension of strategic competition.
Okay, cryptography is a big one. What else?
Simulation of quantum systems. This goes back to Feynman's original idea. Simulating molecules, materials, chemical reactions at the quantum level is incredibly hard for classical computers.
Because they're quantum systems themselves?
Exactly. Quantum computers are naturally suited for this. Think about designing new materials with specific properties or understanding complex biological processes. A huge potential application is optimizing catalysts, like for the Haber process used to make fertilizer.
Fertilizer. That sounds mundane.
But it consumes something like 2% of the world's entire energy output. If a quantum computer could help design a more efficient catalyst by simulating the nitrogen fixation process precisely, the energy savings would be colossal.
Wow. Okay, that's a massive impact.
And we're seeing early examples. IBM reported in 2023 that one of their quantum systems produced better results for a specific materials science problem, modeling properties of a particular magnet, than a state-of-the-art classical supercomputer simulation could.
A tangible result. That's important.
Right. Then search problems. Grover's algorithm gives a quadratic speedup for unstructured search, finding a specific item in a massive unsorted database.
How much faster is quadratic?
It means if a classical computer needs n steps, a quantum computer needs roughly the square root of n steps. So for a database with 1,000,000 items, it's like 1,000 steps instead of 1,000,000. A big deal for very large search spaces.
Like cracking passwords.
That's one application, yes, against symmetric ciphers, where you're essentially searching for the key. Then there's quantum annealing, the approach used by companies like D-Wave. It's good for certain optimization problems, finding the best solution among many possibilities, like in logistics, finance, or computational biology.
Finding the lowest point in a complex landscape.
That's a good analogy. And finally, machine learning. There's a lot of research into how quantum computing might speed up tasks like training certain types of neural networks or developing new generative models, quantum GANs, for instance, perhaps for discovering new drugs or materials.
Okay, a wide range of potential applications, from fundamental science to AI. But you keep mentioning the hurdles. You said earlier they're not practical yet. Let's dig into those challenges. What are the biggest roadblocks?
Right, the reality check. It's crucial. David DiVincenzo laid out 5 key criteria for a practical quantum computer years ago, and they're still the benchmark. You need scalable physical qubits, the ability to initialize them reliably, long coherence times, meaning the quantum state lasts long enough.
Longer than a computation takes.
Exactly. Gates need to be faster than decoherence. You need a universal set of gates, and you need to be able to measure the qubits accurately. Meeting all 5 criteria robustly at scale, that's incredibly hard.
And the physical stuff, materials, control.
Huge challenges there, too. Finding and producing the necessary materials, things like specific isotopes like helium-3 for cooling, specialized superconducting wires, it's difficult and expensive, and then controlling a large system. Imagine needing to send precisely timed microwave or laser pulses to hundreds, thousands, eventually millions of individual qubits, coordinating them with picosecond accuracy.
That sounds like an orchestral nightmare for engineers.
It really is. But the absolute biggest challenge, the one everyone points to, is decoherence.
The noise, losing the quantumness.
Yes, the quantum state is just incredibly fragile. Any interaction with the outside environment, a stray magnetic field, a tiny vibration, even a cosmic ray passing through can disrupt the superposition or entanglement, introducing errors. It's like trying to keep a soap bubble intact in a hurricane.
So you need extreme isolation.
Extreme. That's why most leading quantum computers are housed in these complex dilution refrigerators cooled down to millikelvin temperatures, just thousandths of a degree above absolute zero, colder than deep space. And even then, decoherence happens fast. Studies have shown cosmic rays can knock a qubit out of its state in milliseconds. So any calculation has to be done incredibly quickly before the system just degrades into classical noise. Errors pile up the longer you run.
Which seems to fundamentally limit what you can compute.
Right.
Especially for complex problems that take time.
It's the major bottleneck. Which brings us to quantum error correction.
Like classical computers use. Checksums and parity bits.
Conceptually similar, but vastly more complicated for quantum systems. You can't just copy a qubit to check it, because measuring destroys the state. So error correction involves encoding the information of one logical qubit across many physical qubits in an entangled state.
Using redundancy to protect the information.
Exactly. The theory, that threshold theorem we mentioned, says it's possible if the physical error rate is low enough, maybe around 0.1% or less per operation, but the cost... it's enormous.
How enormous?
Well, estimates vary wildly, but for Shor's algorithm to factor, say, a 2048-bit RSA key, the standard size today, you might need a few thousand logical qubits. But protecting those with error correction could require anywhere from hundreds of thousands to potentially millions of physical qubits. One estimate for a trapped ion approach suggested 3 million physical qubits running for 5 months.
Millions. When we're currently at hundreds, that's a huge gap.
A massive gap. This overhead is why some researchers are pursuing alternative paths like that topological quantum computing idea, hoping it might offer built-in protection against errors.
Okay, so the hardware challenges are immense. What about those quantum supremacy headlines we see? Google, China, are those real breakthroughs or just hype?
Quantum supremacy. Or quantum advantage, as some prefer now. It's a specific benchmark, demonstrating that a quantum device can perform any task, even a contrived useless one, faster than the absolute best classical supercomputer could.
Showing it can do something classically impossible, practically speaking.
Right. Google claimed this in 2019 with their 54-qubit Sycamore chip. They said it did a specific sampling task in minutes that would take the fastest supercomputer, Summit, 10,000 years.
That sounds definitive.
Well, IBM, who built Summit, immediately pushed back, saying Google underestimated the supercomputer, and it could be done in days, not millennia. And since then, classical algorithms have improved further, closing that gap significantly, maybe even eliminating it for that specific task.
So the goalposts moved.
Exactly. Then, a Chinese team at USTC claimed supremacy in 2020 using a different approach with photons called Juzhang. And there continue to be claims and counterclaims and even formal verification efforts using next-gen supercomputers, like a study published in early 2024.
It seems like a constantly evolving race then.
It is. And it's important to remember these supremacy experiments are usually highly specific artificial benchmark problems. They demonstrate impressive quantum control, but they don't necessarily translate directly to solving useful real-world problems any faster yet. The hype often outpaces the practical utility.
So a healthy dose of skepticism is definitely warranted here.
Absolutely. You see this reflected in serious analyses. A 2023 Nature article looking at practical applications bluntly said current quantum computers are good for absolutely nothing right now while acknowledging their future potential. Another article in Communications of the ACM stated current algorithms are just insufficient for practical quantum advantage without major hardware improvements.
Why such strong skepticism despite the progress?
Several reasons pile up. Classical computing, especially with GPUs, keeps getting better, making the target harder to hit. The limited entanglement and coherence in current NISQ machines are major barriers. The algorithms we have often don't map perfectly onto real-world problems or require resources we just don't have. Sometimes clever classical algorithms are found that mimic or beat the quantum ones. They get dequantized. And then there's the massive overhead of error correction if we ever get there. Plus, basic input-output challenges. How do you even feed large data sets into a quantum computer efficiently? Some physicists, like Mikhail Darkinov, are deeply skeptical, arguing the control required for millions of qubits is practically impossible. No, never, as he put it. Others, like Bill Unruh and Paul Davies, have even raised questions about fundamental physical limits based on information density in the universe.
So serious doubts remain at multiple levels. Despite all that, what are people actually building? What do these experimental machines look like?
The two leading physical platforms right now are probably superconducting circuits. This is what companies like IBM, Google, Rigetti use. They've scaled up to hundreds, even over 1,000 qubits, like IBM's Condor chip. But error rates are still relatively high.
Okay.
The other main approach is trapped ions. Companies like IonQ Quantinuum use lasers to hold and manipulate individual charged atoms. These tend to have much lower error rates and better connectivity between qubits, but scaling them up has been slower. Prototypes are more in the tens of qubits range, though improving. Both need those extreme vacuum and cooling systems we discussed. Engineering marvels, but incredibly complex.
Wow. Okay, we have covered a lot of ground. From the weirdness of qubits and superposition, through the history, the potential applications like breaking codes or designing drugs, but also these really sobering engineering challenges and the ongoing skepticism.
It's definitely a field of huge contrasts right now.
Yeah.
Incredible theoretical promise, rapid experimental progress in some ways, but also fundamental obstacles and a gap between the hype and the current reality. We've seen the advances, but also, the reasons for caution about near-term impact and even how we define supremacy.
So let's just clarify one final theoretical point. We've talked a lot about speed, but can a quantum computer solve problems that are fundamentally impossible for a classical computer, regardless of time?
That's a great question, and the answer is generally considered to be no.
No.
In terms of computability, what problems can be solved at all? Quantum computers don't offer any advantage over classical ones. If a problem is undecidable for a classical computer, like the famous halting problem, it's also undecidable for a quantum computer. The Church-Turing thesis, which basically says anything computable can be computed by a standard Turing machine, is believed to hold for quantum computers too. They operate within the same fundamental limits of computation.
Okay, so it's not about unlocking unsolvable problems. It really is all about the speed, the efficiency for certain kinds of problems.
Exactly. It's about time complexity. Computer scientists talk about complexity classes. Problems efficiently solvable classically are in the class P. Problems where solutions can be efficiently verified are in NP. Quantum computers can efficiently solve problems in a class called BQP bounded error, quantum polynomial time. Right. Now, it's strongly suspected, though not yet proven, that BQP contains problems like integer factorization, Shor's algorithm, that are not in P. That's the source of the speedup. But it's also suspected that BQP does not contain all of NP. So quantum computers likely won't be able to efficiently solve all the hard problems whose solutions are easy to check.
So faster for some things, likely hard things, but not a magic bullet for everything.
Precisely. It's about efficiency for a specific, important, but limited class of problems, not infinite power.